Welcome to Session 4 of the Large Language Models course. Today's a turning point. The idea we build today might be the most important one in all 14 sessions. Last time we proved that RNNs struggle to carry information across long distances. Today, we break that limit. Let's look at exactly what breaks. You met this sentence in Session 1. Back then it showed that resolving it needs world knowledge. Today, it shows what that costs in RNN. Read it again. You immediately know that it refers to the trophy, not the suitcase. You didn't even hesitate. To understand what it refers to, you need to remember trophy from 7 words back. For you, that's trivial. For an RNN, it's a fundamental architectural problem. Here's the RNN processing that sentence. 12 words, 12 hidden states. Trophy enters at position 2. H2 carries that information forward. But then H3 arrives, and it partially overwrites H2. Then H4 overwrites H3, and so on, all the way to H12. By the time we reach it at position 9, the information about trophy has been processed, compressed, and overwritten 7 times, and the chain still has 3 more words to run before it stops at H12. The question mark sits on that final state, because that's the summary the model is actually left holding. How much of trophy survives all the way to the end? In practice, often not enough. So what's happening here in one sentence? The same fixed-size state gets overwritten again and again, and distant words quietly lose their voice. The problem gets even sharper in translation. Here's a seek-to-seek model translating I love Paris into French. The encoder processes each word, building hidden states as it goes. And then, this is the critical moment. Everything gets compressed into a single vector. One vector to carry the entire meaning of the input sentence. For 3 words, that's manageable. For a sentence with 30 words or 50, it's a genuine bottleneck. You're asking one vector to remember everything. Notice the decoder now uses only that single vector to generate the entire output. Every French word is predicted from the same compressed summary. Whatever the decoder needs most, where to focus, which input words matter right now, is buried somewhere inside that one vector, if it survived at all. Here's the thing. The encoder does produce a hidden state at every step. We've been throwing them all away, keeping only the last one. That seems like a waste. What if we kept all of them? And this is the key move. What if we let the decoder choose which ones to focus on, dynamically, at each output step? That's attention. Not a new architecture, just a smarter way of using what we already have. Let's make this concrete. We're translating the cat sat on the mat into French. This is the alignment matrix. Each cell tells you how much attention the French output word pays to each English input word. Before I reveal the rows, guess which English word chat will attend to most. Look at the first row. Le, the French article, attends almost entirely to the, 0.85. Chat attends strongly to cat, 0.88. And cest aligns with sat. The diagonal is lighting up. Assise and sur are slightly messier. French grammar distributes sat on differently than English does, but the dominant signal is still correct. The model has learned to look at the right place. Here's the full matrix. Le and tapis, the final article, and carpet, both attend to the and mat. What you're looking at is a learned alignment. The model wasn't told how French and English words correspond. It discovered this entirely from data. So where do those heat map values actually come from? At each decoder step I, we compute a score for every encoder position j. The score is a function of 2 things, the current decoder state and the encoder state at position j. How aligned are they? How relevant? We then run those scores through a softmax. This gives us weights that are positive and sum to 1, a proper probability distribution over encoder positions. The encoder state that scores highest gets the most attention. The others get proportionally less. You might be wondering why we don't just pick the single highest scoring encoder state outright. Softmax keeps this soft on purpose. A weighted blend usually generalizes better than a hard, brittle choice. These weights are the alignment. They encode in a differentiable way which input position the model thinks matters most for this output step. And because the whole thing is differentiable, the scoring function is learned end-to-end from the translation task itself. Now we form the context vector. Take all the encoder hidden states. Multiply each one by its attention weight. Sum them up. That's it. The result is a weighted blend of all encoder states, concentrated on the positions that matter most for this particular output step. And crucially, each decoder step gets its own context vector, computed fresh with its own weights. When we're generating chat, we look mostly at cat. When we're generating tapis, we look mostly at mat. The decoder is no longer stuck with a single frozen summary. The bottleneck is gone. In one sentence, don't compress the input, look back and choose what matters. This idea has a name and a paper. It was published in 2015 by Dmitry Bahdanau, Kyunghyun Cho, and Yoshua Bengio. Neural Machine Translation by Jointly Learning to Align and Translate. One of the most cited papers in deep learning history, over 25,000 citations. The title tells you the key insight. Alignment and translation are learned together, not separately. Before this, people had tried to help translation models by manually defining which words should align. Bahdanau's team showed you don't need that. The model learns the alignment function itself, purely from seeing translation pairs. Notice, translation quality jumped, not because the model got bigger, but because information could now flow freely from any input position to any output step. The architecture got smarter, not heavier. The problem we inherited from session 3 is solved, but a sharper question starts to form. We're still using RNNs on both sides. The encoder still processes words sequentially. Why stop here? But Bahdanau's formulation has a limit. It uses a bespoke scoring function tied to the sec2-seq setup. In 2017, a cleaner, more general formulation appeared in the Transformer paper. Vaswani and colleagues. Next session is entirely about it. It comes with a new vocabulary, one you'll use for the rest of the course. Query, key, value. Think of a library. You walk in with a question. Say you're hunting for books on attention mechanisms. You scan the spine labels on the shelves. The spines are the keys. They tell you what each book is about without you having to open them. The actual pages inside are the values. You pick the books whose spines best match your question. Here's the same picture as a mechanism. The query, Q, is your question. The keys, K, are the labels you compare against. Dot product, the simplest measure of similarity, tells you how well each key matches the query. It's the same kind of comparison as the cosine similarity from session 2, just without normalizing for vector length, which is part of why we'll need to rescale it in a moment. The higher the dot product, the better they line up. Run the scores through softmax, and you get weights that sum to 1. The best matching key takes most of the weight. The others share the rest. Multiply each value v by its weight. Sum. That's the output, a blend of all values, concentrated on the ones whose keys matched the query best. This is the library. You asked a question, matched it to spine labels, and came away with a weighted mixture of relevant content. Before we use a query and a key, we should ask where they come from. Attention has to measure how much one word matters to another. So here is the obvious move. We already gave every word a vector back in session 2. Word 2 vec and glove. Why not just compare those embeddings directly, dot product one against another, and call that the attention score? Because those vectors were trained for a different job. Word 2 vec learned them by predicting nearby words. That objective pulls words with similar neighbors close together. That's exactly what we wanted in session 2, but nothing in it ever asked those vectors to be good at the comparison we need now. Two words can be close as neighbors and still play completely different roles in a sentence. The sits near almost everything, but almost nothing in a sentence is about the. So the comparison needs its own space, a space where relevance really is a dot product, and we can't hand design that space. Nobody knows what its axes should be. The model has to learn it. Here's how that space gets learned. We introduce one matrix per role, and each one is shared by every word in the sequence. Multiply a word's embedding by WQ, and you get that word's query. Multiply the same embedding by WK, and you get its key. Take 3 words. The cat sat. Each one arrives as an embedding. X1, X2, X3. This is what session 2 handed us. Now, watch the arrows. Every word goes through the same matrix, WQ, and comes out as a query. Notice what is not on this slide. There is no separate query matrix for cat and another for sat. One matrix used by all 3 words and by every other word the model will ever see. We do the same again for keys, with a second shared matrix, WK. Every word now has 2 representations, a query, for when it's doing the asking, and a key, for when it's being asked about. And a third shared matrix, WV, gives every word a value, the content it will actually contribute if another word decides to attend to it. 3 matrices, 3 roles, all shared. You might be wondering how we choose the numbers inside them. We don't. They start random and are learned by backpropagation from the task itself, exactly like every other weight in the network. Let's write that first mapping out. Qi equals WQ times Xi. Word I's embedding multiplied by the shared query matrix. The embedding lives in RD. The query it produces lives in a smaller space, RDK. The space queries and keys share, so their dot product actually means something. Same shape for the key. Ki equals WK times Xi. WK also maps RD down to that same RDK, so every key can be compared against every query in exactly that shared space. And the value, Vi equals WV times Xi. Same recipe, same shared matrix, reused across every word, the third and last of the 3. Let's continue this exact block. Same block we just built, picked up right where we left it. Now every query is about to be compared with every key. 9 chips, 3 shared matrices, exactly as we left them. Start with SAT's query, Q3. Its first comparison against K1, thus key. See that small circle above Q3, connected to both of them? That's Z3, 1, the score for that pair. Second comparison, Q3 against K2, cat's key. We'll call this one Z3, 2. And Z3, 3, Q3 against K3, its own key. Every query, and I do mean every one, compares against every key, itself included. Now, the same thing happens for every other query. All at once. This query runs against all 3 keys. So does cat's. 3 groups of 3, 9 score nodes in total, 1 for every possible query key pair. Let's name that score. Z sub I sub j equals Qi dotted with Kj. The query of word I against the key of word j. 1 number for every pair. That's the identity every one of these 9 circles stands for. 9 raw scores aren't weights yet, so let's turn them into some. Each group of 3 feeds through its own softmax. Here's where we left off. 3 groups of 3 scores. For each query, its 3 scores feed into their own softmax. Out come 3 weights, alpha, that sum to 1. Notice each softmax box now carries its own query's index, softmax 1, softmax 2, softmax 3, matching the alphas it produces. Follow one query all the way through. SAT's 3 weights, alpha 3, 1, 2, 3, arrive from below. The same 3 values, V1, V2, V3, arrive from the right. Both feed into one output unit, SAT's weighted sum, Z3. The same construction happens for every other query. I've drawn it faint here so the one clean example doesn't get lost. 3 output units in total, 1 per query, each one its own weighted sum of the same 3 values. Let's name that normalizing step precisely. Alpha ij equals softmax over j of zij. Take the raw scores for query I, turn them into weights that sum to 1, exactly what just happened, 3 times over. And the identity that names the whole mechanism. 1 subscript now instead of 2. Zi equals the sum over j of alpha ij times vj. Every value, weighted by how much attention it earned, summed into one output. Same values, different weights, different outputs for every query. Here is the formula. The same Zi you just built, but for every word at once. Q, K, and V now mean the whole stack. every word's query, key, and value gathered into one matrix. 4 pieces, 1 equation. QK transpose, dot product of every query with every key. You're computing a similarity score. Large when the query and key point in the same direction, small when they're orthogonal. This is the alignment signal, divided by the square root of dk, the key dimension. This is the scaled in scaled dot product attention. And it's the rescaling I promised you back on the library slide. In high dimensions, dot products naturally grow large, which pushes the softmax into regions of very small gradients. Dividing by the square root of dk keeps the scores in a healthy range. Then, softmax. And you've seen this move twice already. Raw scores in, a probability distribution out. The highest scoring key captures most of the weight. The weaker matches keep a sliver, and everything sums to 1. Times V, the weighted sum of values. The output isn't just the best matching value, it's a blend of all values, with the blend controlled by how well each key matched the query. One elegant matrix multiplication, and you've already built every piece of it by hand. Watch this play out. Keep your eye on the gold arrow. That's the query. On the left, the 3 colored arrows are the keys. The query rotates toward each one in turn, and as it aligns, a score appears in the table. Key 2 is nearly parallel. It scores 8.6. Key 3 barely aligns. It scores 1.2. You know what comes next. Softmax converts those raw scores into weights that sum to 1. Key 2 takes 0.82 of the total. The others share the remainder. Now watch the value bars. Each one shrinks in proportion to its weight. Key 2's value passes through almost intact. The others fade. Sum them, and that green bar at the bottom is the context vector. The output. Exactly what the formula says. Softmax of QK transpose over root dk. Let's push this idea one step further. Look back at the cat set. Every query compared against every key from the same 3 words. That was already self-attention. We just hadn't named it. Bahdanau's version connects 2 different sequences, encoder to decoder. But nothing requires 2 sequences. One sentence can attend only to itself. That's self-attention, and it gets far more interesting once pronouns are involved. Read this sentence. Who is he? The dog or the man? Every other word, dog, man, angry, all of them can act as a key that he compares itself against. He sends out a query. The dot products tell us which keys best match it. Dog scores 72%. Man scores 18%. The model attends mostly to dog, because dog is the grammatical subject, and the context of angry is most consistent with a dog biting rather than being bitten. Every token can attend directly to every other token. No recurrence, no fixed window, no information bottleneck. Distance is completely irrelevant. He can reach dog across 5 positions just as easily as reaching the word next to it. If you take one sentence home from today, take this one. Every token gets a direct line to every other token, and the model learns which lines are worth listening to. Step back for a moment and ask what kind of computation we've just built. This is the unit you know. Inputs arrive, each is multiplied by its own weight, the results are summed, and activation squashes the total. The weights W1, W2, W3 are parameters, learned during training, then fixed. The recurrent unit adds one thing, its own previous output, folded back in through a second matrix, U. That's what gives it memory. But notice, W and U are still parameters, still fixed after training. The unit cannot tell you how much of H at time t came from the word at position 3 versus position 7. It only has the accumulated total. The attention unit breaks that pattern. Its incoming connections still have weights, alpha 2-1, alpha 2-2, alpha 2-3, but look where they come from. They're computed at runtime from the words themselves by the query key dot product we just wrote down. Thick line, large weight. Faint line, small weight. Feed the same unit a different sentence, and the weights are different. There's the whole story in one row. Fixed once trained, also fixed. Computed per input. That's the structural break. Instead of producing an output from the activations of the previous layer through fixed parameters, This unit explicitly models the relationships between all the words and lets those relationships set its own weights. Let's put it in a table. Walk the rows with me. Path length between tokens. For an RNN, it's O of n. Information travels through every intermediate state. With attention, it's O of 1. A direct connection, always. Long-range dependencies, degraded with distance in RNNs, preserved exactly with attention. Can you parallelize it? Not in RNN. It processes one token at a time by definition. That was never just about memory. Attention, yes. Every position computed simultaneously. And the fixed size bottleneck, built into seek-to-seek with RNNs, completely gone with attention. The information bottleneck is gone. Any word can talk directly to any other word, no matter how far apart they sit. And I want to be precise here. This isn't a marginal improvement. It changes what these models can learn. But, and there's always a but, we've got two new problems. The direct connections are real. We've earned them. But this box is holding two things open. Two jobs attention doesn't do. Let's take them one at a time. First, attention has no positional information. You might be thinking, surely word order matters somewhere in this pipeline. It does, just not inside attention itself. That gap is exactly what session 5 closes. Attention treats the sentence as a set, not a sequence. Scramble the word order. Angry was he because man the bit dog the, and the attention weights are mathematically identical. The model can't tell that dog comes before bit. Second, every model we've actually built still leans on RNNs. Bahdanau Attention wraps attention around an existing seek-to-seek architecture. We've shown attention comparing tokens directly in the cat sat and in the dog bit the man, but we haven't yet shown a complete model that drops the RNN and lets attention do all the work. And that raises the natural next question. What if we threw away the RNN entirely and built everything from attention alone? Let's place today on the map. Sessions 1 through 3. We started with the question of why language is hard. We gave words coordinates, word vectors. We learned to process sequences with RNNs and LSTMs. And then, last session, we hit the wall. RNNs can't carry information far enough. Today, session 4, we broke through that wall. Attention gives any word direct access to any other. 10 sessions left. Session 5 is next, the transformer. We know what it needs to solve. Positional information. No more RNNs. One more thing before the lab. We still have an RNN in the room. Next session, we throw it out entirely. Attention is all you need. In today's 2-hour lab, you'll implement this from the ground up. No black boxes. Part 1. You implement scaled dot product attention in PyTorch. No NN multi-head attention. Matrix multiply queries and keys, scale by root DK, softmax, apply to values. Get the shapes right. It's fewer than 10 lines. Part 2. Visualize the weight matrix for a short sentence pair. Plot the heat map. Watch L attend to the, chat attend to cat. You'll see the diagonal pattern emerge from scratch. Part 3. You scramble the input word order and watch what happens. The attention pattern shifts, but so does the meaning. Something is missing. The model has no way to know that word order changed. The challenge. Can you figure out what information attention needs but doesn't have before session 5 tells you? Write it as a comment in your notebook. Next week, we'll see if you were right.